All right, ordered pairs can be used to show inputs and outputs. So if you look where the X normally is in an ordered pair, okay, those are now called inputs. And where the Y normally is in an ordered pair, those are now called outputs. Typically in a function, you're going to input the X variable, you're going to do some operations to it, and then it's going to output the Y variable. Okay, so inputs and outputs. The X is called the input, the Y is the output. So there's some vocab to start off with. Here's some more vocab. The X value is also called the independent variable, and the Y value is called the dependent variable. Now, we just talked about, I mentioned independent probability and dependent probability with the events. Not the same thing, but similar if you think about the words. Independent means that's the reason it's called independent is because that's the value I usually plug in. So I get to choose what I want that value to be. And then whatever I plug in, the Y value is going to output. The output is going to be dependent on whatever we inputted for the X value. So that's why it's called the independent, and the dependent variable is the Y value. All the possible X values, that should say values, are called the domain. And all the possible Y values are called the range. Now, we're not going to do an awful lot with domain and range this year. You'll have some questions next year in your Algebra 1 class where they ask you, but the domain is all possible X values. So if you have a linear function like the ones we talk about this year, where it's just a line, that line extends forever in both directions. So asking you to find the domain and range is going to get pretty repetitive. The domain is all possible X values. It's going to go on forever to the right. It's going to go on forever to the left. The range is all the possible Y values. That line's going to extend forever up, and it's going to extend forever down. So it's also all possible Y values. That's why we don't get into domain and range very much when we're talking about linear functions, but you're going to see some examples of some nonlinear functions, and they are going to either stop, where it's just like a certain number of points, or maybe it's a parabola, like this shape here, and it doesn't go down forever. And so it would have there would be a minimum value on that parabola, and then that would affect if I'm doing the Y, that would be my range. So you'll talk more about that next year. We'll look at it some today, but I don't think you're going to have any homework questions about that, because we're going to be looking at linear functions primarily this year. So names for the X variable. We said you can call it the input. Whereas the Y variable is the output. We also said the X variable can be called the independent variable. I'm going to abbreviate variable. And then the Y value would be the dependent variable. We also said if you're talking about all the possible X values, that's called the domain. And if you're talking about all the possible Y values, that's called the range. Not the range that you find when you're doing mean, median, and mode, where you subtract the largest number minus the smallest number. That's not, it's literally a list of all the possible Y values. Or you could say everything greater than 2 or something like that. And then there's one more I want to add, and you are already familiar with this, but when we're talking about slope, we refer to the X coordinate as your rise, or sorry, that's the run. The run, did it backwards because it's Y on top. And then the Y is the rise. So that's going to come into play later on this chapter when we start talking about linear functions again. We talk about slope. So the rise is the change in Y. The run is the change in X. And so if you ever see delta Y, or delta x. That means change in y over change in x. And so some high school textbooks will say m for slope. Oh, I just gave you one of the homework problems from the 3.5 algebra 1. It'll look like this: delta y over delta x, change in y over change in. It means rise over run. That's what they refer to it in advanced classes. They don't say rise and run, but I like rise and run. All right, so our next vocab word is relation. A relation pairs inputs with outputs and can be represented by ordered pairs or by a mapping diagram. So relation is a group of ordered pairs. In this case, it's 3, 0, 1, 1, 2, and 2, 4. Or you can show those instead of as ordered pairs, you can use a mapping diagram and say when you input 0 for x, it's going to output 1 for y. When you input 1, it's going to output 2. When you input 2, it's going to output 4. Okay, so that you could also use a mapping diagram. And so what we're going to do is I'm going to give you some, we're going to go back a couple chapters or a lot of chapters ago. We're going to talk about area, perimeter, circumference, volume. And I want to, as we're filling out these mapping diagrams, we can relate it back to something that we might have remembered from a few chapters ago. So I've got here this rectangle with an area of A. The x value is the length of the rectangle. When you input 1 for x, what is it going to output for the area? This isn't supposed to be a complicated question, Owen. It's going to output 2. When you plug in 1 for x, area of a rectangle, of course, length times width or base times height, 1 times 2 is 2. When you input 2, what's the output going to be? Carson? 4. When you input 3, what's the output, Brady? 6. And when you input 4, we can see the pattern. It's going to output 8. So although you won't have to do it on tonight's homework, one of the questions we're going to see in section 6.4 is you're going to have to write a linear equation for something like this. So let's see if we can write a equation that's in slope-intercept form. So there's my slope-intercept equation. I'm going to get this up here. There's my slope-intercept equation. The output variable, which is normally the y, they are relabeling it as capital A for area. What are we multiplying x by? Xander? 2. So our m value would be 2. So y equals, or a equals 2x. Are we adding anything to this? No, so just leave it like that. So this is in slope-intercept form. It's just there's no b value, which means the b value is 0. Do you remember what happens when the b value is 0? If I were to graph this, what does that look like, Julia? That's exactly right. It starts from the origin. And that makes sense. If I don't have a length, if my length is 0, I'm not going to have an area. So 0, 0. It makes sense they would start there. So there's my slope-intercept function for this area of this rectangle, because not all rectangles are going to have a width of 2. Okay, so let's move down to the perimeter of that same rectangle. If you, and this might take you a little bit more time to think about it, if you input 1 for the length, what is that going to output for the perimeter? Lizzie? 6. Nice job. So we're obviously adding the x with another x up here and then another 2 over here. Or another way to think about it is you're going to take x plus 2 and times it by 2, right? To find the perimeter, because once you add the length and width, you double it and you got the other length and width. So what is my output going to be if I plug in 2? Lucy? 8. What's my output going to be if I plug in 3? Dawson? 10. And the rest of it, you can see that last one's just going to be a 12. It's following that same pattern. So as before, we're increasing by 2 every time we input something. Every time the input increases by 1, the output is increasing by 2. That is because if I distribute this, we get 2x plus 4. And so my function, instead of being a equals 2x, is now a equals 2x plus 4. So they have the same slope. But what's different is that this one's starting at 4 for the y-intercept instead of 0. Now, if you're wondering why this doesn't say 4, then that's because we're not plugging in 0 for x, we're plugging in 1 for x. So now it's at 6. It starts at 6, then 8, then 10, then 12. Okay. So this time there was something we were adding onto it. Okay. What about circumference? What's the circumference formula, Xander?
Pi equals or pi times r squared.
That's the area formula. Pi times diameter. Good. Yeah, my other Math 7 students have a test over that tomorrow, so I've got them up on the board there. You can see the circumference and area on the board there. So pi times diameter, but they're giving us r. So I have to write my function in terms of r. So how do I change this? Is there another circumference formula I could use, Julia? 2 pi r. Yeah, and so this is a common one that people use when they have the, I'm a fan of just using pi d because it's shorter, but 2 pi r is the same thing. Take the radius, double it, times by pi. So my function here is going to be c equals 2 pi r. Is that in slope intercept form? It is. It is in slope intercept form. Because there's my r. Now my r is in the place of the x, right? So we're renaming, instead of x, we're calling the input r, and instead of y, we're calling the output c. Okay. But 2 pi is just a constant. 2 pi is a number. And the number in front of the x is called the m. Y equals mx plus b. So yeah, this is just a different looking, but yeah, it's in slope intercept form. It's, you could say c equals 2 pi r plus 0, because if you don't have a radius, you're not going to have an area. So it makes sense that as Julia mentioned before, this is going to start at the origin. So when I plug in 1 for the radius, let's write our outputs in terms of pi. Save us some work. When you plug in 1 for the radius, what's 1 times 2? Sky? 2 and then times pi? Oh, yeah, 6.28. But if we just leave it in terms of pi, you could just say 2 pi. Yeah, we'll do that because I don't want everyone to have to think about what 3.14 times 2 is or times whatever. So if you plug in 2 for the radius, what's 2 times 2? You could shout it out. It's fine. 4. Okay, so 4 pi. So as the radius increases by 1, the circumference is going to have a doubling effect because we're doubling the radius to get the diameter each time. And then the next one's going to be 6 pi. And then 4 times 2 is 8. So this would be 8 pi. How about this one? What's a function rule or equation we could write for the volume of this rectangular prism? For this one, I'll give you a hint. The formula that you would use for any rectangular prism is capital BH, capital B, of course, being length times width times height. Now, we know what the length and width is. So what can we simplify those two, Maddox? Exactly. The volume is just going to be 9 times h because the length and width are both 3. It's a square prism. So if I plug in 1 for the height, what's 9 times 1? Anybody? 9. 9 times 2? 9 times 3? 9 times 4. Okay, thank you. All right. All right. Let's move on to the next part then. This is going to seem like just a way too simple task, but I'm going to ask you to tell me what coordinate points or what ordered pairs you'd be able to write from that mapping diagram. When x is 1, what is y? 3. So the 0.13 is one of the points in that relationship, that relation. What about when x is 2?
6,
When x is 3?
9,
When x is 4? Okay. Pretty simple stuff, right? Just
Yeah.
follow the arrows. Example B. When x is 0, what's the output? 0. When x is 2, what's the output? Julia? Yeah, so I need to list them both. When x is 2, y can be 1 or y can be -2. What about when x is 4? Shane? -3. Okay, so now we've practiced using the mapping diagrams with these shapes here, like how we'd fill in the missing values of a mapping diagram. Now we've talked about how to write the ordered points, ordered pairs from a mapping diagram. You'll notice again, this is interesting. We're going to talk about this in a moment. The x value or the input of 2 had 2 different outputs. And so that's actually going to tie into where we're heading next. A function is a relation that pairs each input with exactly 1 output. A function is a relation that pairs each input with exactly 1 output. Does every one of these inputs have 1 output? Yes, this is a function then. Does every one of these inputs have exactly 1 output? No, so this is not a function. That's how you can tell it's not a function. We have the input 2 going to 2 separate outputs. Doesn't mean that this doesn't exist. It does exist. I can plot these 4 points for sure, but they're not going to form a function. Not every function has to be linear either, although we are going to talk about lots of linear functions. That's what our particular pre-algebra unit's over. There are nonlinear ones too that we'll look at. But yeah, just because it doesn't form a line doesn't mean it's not a function, but that means it's not a function if you have 1 input going to 2 or more outputs. What about this one? Is this one a function? Sky? It is. According to the definition, every input goes to 1 output. Sure, 10 is being used twice, but does 5 have 1 output? Yeah. Does 12 have 1 output? Absolutely. So this is a function. What about this next one? Is this a function, Xander?
No.
What makes it not a function?
0 has 2 outputs.
Yes, 0 has 2 outputs. So just to be clear, it's not because there's a crisscross going on up here with the -2 and the -1. That doesn't matter at all. You have 1 input having 2 different outputs. So all you really have to do if you have a mapping diagram like this is check your arrows. Does every input have exactly 1 arrow coming out of it? And I don't care where the arrow points to. Yes, this one does. This one does not, it has 2 arrows coming out of the 0. Again, I don't care where the arrows point to, but if you see 2 arrows coming out of an input, then it's no longer a function. What about this example? Chloe, is this a function or not a function? Why is it a function? Not a function. Why is it not a function? There it is. Yep, 2 has 2 outputs. So this is not a function. It's just like the last one we looked at. Yeah, so again, don't look at the output column because every output has an arrow going to it. But that's not what it means to be a function. To be a function, every input can only have 1 arrow coming from it. Now, what gets a little bit more tricky is when you take the mapping diagram away. How many coordinate points are here? How many coordinate points are here? It's not 3. There's 4. 1, 4, 2, 0, 2, -5, and 3, -6. It's easy when you see the arrows. There are also 4 coordinates here. but no arrows. So if I'm giving it to you as what we call a input-output chart, or I call it a T-table, you're not looking for arrows now. What you're looking for is repeat X values. Because if we look up this last one we did here, where we had to write the coordinates, you'll notice there was 2 repeating X values, and this is clearly not a function because of that, right? Because of the 2, 1, and then the 2, -2, having 2 different outputs there. So I'm looking for repeating X values. Do I have repeating X values? Yes. So this is not a function. How about this one? Do I have repeating X values? No. So I don't even care what the Y values are. This one would be a function. How about this one? Do I have repeating X values? Yes. So what do you say? Function or not a function? This one is a function. Why? Brady? Yeah, they just listed the same. Yeah, so we have to be careful. Maybe we should modify this. Just because we don't, we see 2 repeating X values doesn't necessarily mean there's that it's not a function, as long as the Y values are also the same. So what we have here is just a point laid on top of another point. So 4 goes to 3. If I were mapping this out on a map diagram, I wouldn't even draw 4 twice. I'd put 4, just have 1 arrow. There's just 1 arrow coming out of the 4 here. So this one is a function because the Y also repeats. I had to put that in there because I wanted to trick some people. Yeah, but you could see that. They could list a point, coordinate point twice. Next example. Describe the pattern of inputs and outputs for each mapping diagram. Is the function linear? First of all, is this a function? This one is a function. Next question, is it a linear function? Jimmy, you're nodding. How can you tell it's a linear function? Okay, that's a good point. Now, actually, that doesn't mean that it's linear, but that does mean it's linear, but it's not the only thing that you would have to check for. Okay, so what he said is it's linear because the output's always 15 times the input, which means if I were to write the equation for this one, the output Y is always 15 times the input. Is that an equation of a linear function? Yeah, it's in slope-intercept form. And what's the y-intercept for this function? Sky? 0. Yeah, it goes to the origin. Okay, so this one's totally linear. Just because it's a function, and it is a function, doesn't make it linear. So I see that there's 1 arrow coming out of each of them. So this is a function. Then I have to check to see if it's a linear. And here's the best way to see that if it's linear. If you have a line, the slope is always going to be constant, no matter where you are on that line. If the slope changes, your line's starting to get steeper or not as steep, which means it's not a line at all, it's a curve. It's starting to curve. We don't want that. So to see that your slope is constant, you can see that we're increasing by 15 for the output. When you rise 15, you run 1. When you rise 15, you run 1. Someone's duck's going off.
Oh, that's my phone.
And when you rise 15, you run 1. I'm glad we got interrupted by a potential spam call. Now, did you silence your phone? Thank you.
At least it was in the back.
It's true. Okay. So the slope is 15. But here's why Jimmy's method is not perfect. Because if it has a y-intercept other than 0, the output's not always going to be 15 times the input. It just so happens to be because this one's also called a direct variation. Remember, we're talking about direct variations, proportional relationships back in our chapter 4. That's what this one is. Just because it's so Jimmy's way of checking tells you it's a direct variation. Well, of course, that's going to make a line then. But not all lines are going to go to the origin. So we want to check this way. We want to check to see if our slope is constant by checking the increase in y or decrease, change in y over the change in x. Is this a function? Yes, this is a function.
Yes.
It has one arrow coming out of every input, correct? This one's a function. This one was a linear function. Doesn't mean this next one's going to be, but it could. Do you think this one's linear, Xander?
Yes.
Okay, why do you say that?
Because each time the input moves or adds 2, the output decreases by 3.
Okay, so we're rising, actually falling, right? Remember the rise is the change in y, so we're going down 3 over 2, down 3 over 2, down 3 over 2. If that's the same all the way through your chart, then you have a linear function. And the equation for this linear function would be what? What's the slope? Down 3 over 2. What's the slope? Jimmy? Good. Negative 3 over 2. What's the y-intercept? Xander?
6.
Not 6. Was he? Not 4. Y-intercept, Deegan? It's 9. The y-intercept is the b value, and the b value is the y coordinate when this x coordinate is 0. Because if I'm on the y-axis, the x coordinate is 0. Do they give me my x coordinate being 0 up here?
No.
They do not. So, but if I reverse this and go backwards twice to 0, I'd have to add 3, and that's where Deacon gets 9. Does that make sense? Okay. Again, this is not something they're going to ask you to do on tonight's homework, but it is something I'm going to ask you to do in a couple sections where you have to tell if it's a function, if it's a linear function, and if it's a linear function, you have to write the equation. JC, you with us back there? Okay. So both of these were linear functions. Now, not to harp on Jimmy any more than I already have, but do you see why Jimmy's method of seeing if the output is always a certain constant being multiplied to the input? That doesn't work here because you could say, well, they're just timesing by 3 to get 6. Are they timesing 4 by 3 to get 3? No, but that doesn't mean it's not linear. It just means it's not a direct variation. So there's a difference. So this method of checking your rise and your run is always going to tell you if it's linear or not. I bring that up because I see that mistake made a lot. Okay. The last part about this isn't something you're going to see in tonight's homework, but you might see it on your quiz next week. It's called the vertical line test. So we've been telling whether they're functions or not by looking at the coordinates, whether it's a mapping diagram or even a t-table. You can also, in fact, it's much easier to tell if it's a function if you look at the graphs. So the vertical line test says a graph represents a function when no vertical line will pass through that through more than one point on the graph. So you can see this would be a function, even though it's not connected, also not linear. This is a function because if I draw a vertical line anywhere on that graph, it's not going to cross 2 points. It's only going to cross 1. Whereas if I draw a vertical line anywhere on this graph, it's definitely, most often, going to cross at 2 different spots. So this would not be a function. What we have here is we have one x value going to 2 different y values. This is what we're looking at. And we know this is a no-no. So if I have a mapping diagram, sure, I can look at the arrows. But if I have a graph, just see if there's any spot on that graph, you can draw a vertical line. And if you see 2 different y points on, if you draw that line, you see it cross 2 different spots, you know it can't be a function. So what about this one? Is this a function? Can I draw any vertical line that would pass through 2 or more points? Xander?
It's not a function.
Why do you say not?
Because at x coordinate 5, you could draw a line. Oh, and 2 actually. You could draw a line there, and it crosses 2 points.
You're absolutely right. And all I need is one line. All I need is one line I could draw anywhere that crosses 2 points. I got 2 lines I could draw here. So this is definitely not a function. So I'm going to say no. We'll say no function. There we go. What about this one? Is this a function? Yeah, I can draw a vertical line anywhere I want to. It's only going to cross 1 spot. So this one is a function. In fact, more than that, it's a linear function. And what would the equation of this linear function be? Owen? Ah, very close. I agree with your 1. It's rise 1. There we go. 1/2 x plus 1. Do you guys remember doing this? We had to figure out what the slope is, figure out where it's crossing the y-axis, then we had our slope intercept equation. Okay, so this one's a function, and I have a linear. Every time it's a linear function, I'm going to ask you to write the equation because I think it's good practice. What about this? Is this a function? Can I draw a vertical line that's going to cross 2 points? Nope. I can only draw vertical lines that will cross through 1 point. So this one is a function. Is it linear? No. I guess I was using the word yes, wasn't I? Yeah, it's a function. It's not linear. It's not a linear function. So what about this one? Is this one a function? No. How about that line right there crosses 2 points? This one's not a function. Again, very easy to tell if it's a function just by looking at it. What about this one here? Function or no function? What do you think, Jace?
No.
I agree. No function. I can draw lots of vertical lines on the right side as you go farther right, especially. It's going to cross more than one spot. So that's not a function. What about this one here? Martin, what do you think? Function or no function? But Martin, I can draw a line right here and it only crosses the graph once. Martin. That's true. It's any vertical line. If I can think of any vertical line that's going to cross twice or more, then it's not a function. So this one's no. Doesn't pass the vertical line test. What about this one here? Function. All right, function. Good. And this guy right here? Xander?
Yeah.
Yes, also a function. Yep. Every time I draw a vertical line, it's only going to cross one spot. So yeah, again, something else that's a preview to what you'll be doing in your Algebra 1 textbook next year, but a really simple thing to do. Yes.
So usually you could draw any line imaginable.
Any vertical line.
Any vertical. Oh, never mind.
So here's a good point. If I draw a horizontal line, does it cross more than one time? Yes. Okay. But am I allowed to have an x coordinate going to a y point with another x coordinate going to it? Is that legal? Yeah.
Sure.
I can have a bunch of different x's going to the same y as long as there's only one arrow coming out of each x. That's what I'm looking at here. I've got multiple x's giving me the same y value. Fine. What I can't have is one x value going to two different y's. Not fine. You see the difference there? Now, this is a function. Hang on. This is a function. This function is not 1-to-1. They call a functions like this linear function here. This would be a 1-to-1 function. This one's not a 1-to-1 function because I got two x's going the same y, but it's still a function. So that still qualifies.
I need the following students to come.
All right, you're dismissed.
Levi Shoemaker.
Section 6.1 homework is on big ideas. No work paper for 6.1. So when you're done, just hit turn in on the Google Classroom. You don't have to attach anything.